Hey, Statistics 1 students. So this is a lesson on the concepts of weight and a new thing called apparent weight. And in this discussion, I'm going to differentiate once again between mass and weight, which is a gravitational force that acts on an object, and this new quantity called apparent weight. And toward the end of the video, things are going to get a little bit weird, I'll just say, in terms of some of the claims I'm going to be making, but I will try to make them a little more palatable to you, these ideas, these claims in class on Monday. So first of all, let's think about the following. I'm imagining a person over here who is standing on a bathroom scale or a scale at the doctor's office. And the question is, what does a scale measure? What does a scale measure? Pause the video for a moment and take a hypothesis. Okay, well, most people in this situation with this question will say, oh, a scale measures your weight, right? You stand on a scale and then you know how much you weigh. Pounds, or I suppose the scale could be calibrated to record a value in newtons. But that's actually not the case. It is true that what a scale measures is numerically equivalent to your weight under ordinary circumstances, I'll just say, but it's not directly measuring your weight. So I'll try to explain this. This is a person of mass M, let's say, okay, and maybe their mass is 100 kilograms. That's a pretty big mass for a human being, but 100 kilograms. And they're standing on the scale over here, and there are two forces acting on this person. There's a gravitational force pulling the person down, and there is a normal force pushing the person. Now, we know that that gravitational force is just equal to their mass, which is how much matter, how much stuff is in their body, times the Earth's gravitational field. Using the approximation that we're allowed to use, little g, the Earth's gravitational field being 10 newtons per kilogram, we find that this person's weight, that is the gravitational pull on them on Earth, is 1,000 newtons. And here's the thing, because this person is not accelerating, because they're not accelerating, I know that there's no net force on them. And therefore, this normal force must also be 1,000 newtons, which cancels out with the gravitational force pulling them down, and there is no net force on them. Their velocity of 0 in this case remains constant. The scale reads, not surprisingly, 1,000 newtons. And that raises the question, well, is the scale displaying the person's weight? 1,000 newtons is definitely equal to the person's weight in this example, but the normal force is also 1,000 newtons. So which is it? Is the scale measuring their weight, or is it measuring the normal force that the scale itself is exerting on their body? I think I can convince you pretty easily that it's actually measuring the normal force. For instance, what if this same person were standing on the scale and another person comes by and pushes their head down, okay? This person says, I push with 500 newtons of force. All right, now there are three forces acting on the person. There is a 1,000 Newton downward gravitational force, that's their weight. There's also a contact force from the person's hand of 500 newtons. And now, again, their acceleration is 0, so the net force on them is 0. So the normal force now to cancel out those two downward forces must be 1,500 newtons. What does the scale read? The scale reads 1,500 1,500 newtons. Not 1,000, but 1,500. Now, you might think this is kind of an artificial situation. I mean, who's going to push down someone's head standing on a scale? But conceptually, it is important, and it will be important momentarily to appreciate that it's not the object's weight that is displayed on a scale, but merely the normal force that the scale itself has to exert upward to support whatever object is sitting atop it. So yeah, you put an object on a scale, you press down on the object, and the scale reading goes up, even though the weight of the object hasn't changed. The object still has the same mass, the Earth's gravitational field hasn't changed. So I'll answer the question that I posed above. What does a scale measure? A scale measures the normal force that the scale exerts on an object. Okay, great. So what is a situation that's maybe a little more organic in which the normal force on a person is not equal to their weight? Well, I'll preview here a little bit. If the normal force on your feet is not equal to your actual weight, you actually feel like you weigh a different amount in that situation. You feel as though you weigh more whenever the normal force on your feet is more than your weight. You feel that you weigh less when the normal force on your feet is less than your weight. When I was teaching physics in New York, I would ask people this. I'd say, what's a situation throughout the day where you might feel a little lighter than usual or a little kind of heavier than usual? And this doesn't work quite as well in the Palos Verdes area. But can you think of a situation where you feel lighter or heavier than usual? Pause the video and think of that. Okay, maybe you said an elevator. In New York, there are tall buildings, right? Everyone has an elevator either in their where they work or their school even, or their apartment building. When you're in an elevator, you tend to feel heavier or lighter than usual, depending on what the elevator is doing. So I'm going to draw 3 instances of an elevator here. Let's see if I can duplicate this picture. There we go. Okay. And in all 3 of these pictures that I'm drawing here, there's a person standing inside. Person, person, person. And I'm going to imagine that the person is moving up in each of these pictures. In each picture, the person's moving up. So maybe the bottom picture, they're in the lobby of an apartment building, and the top picture, they're on the 15th floor where their apartment is located, right? A typical elevator ride works like this. When you leave the lobby floor, well, you're not moving, and then you start to pick up speed in the upward direction. So during the first part of this upward elevator trip, your velocity is up and you're speeding up. That means your acceleration is up. Then during the middle of a long elevator ride, you're actually not accelerating. You're just cruising up at some constant upward velocity. Finally, as you approach the top floor that you're intending to get off at, the elevator has to slow down. So it eventually stops and you can walk off. In order for the elevator to slow down, it has to accelerate downward. All right, let's just pick some numerical values here. Maybe the elevator has a 1 meter per second squared upward acceleration as it picks up speed, and it has a 1 meter per second squared downward acceleration as it slows down at the top. Notice at the top and the bottom picture, the person's acceleration is not 0. So the forces acting on them will not cancel out. The normal force on their feet will not equal their weight. Let's draw in those forces. Suppose the mass of the person is, once again, 100 kilograms. All right, so in each picture, there's a gravitational force pulling them down equal to 100 newtons. That is just their weight. Their weight is 100 newtons. Okay, and in this middle picture, when they're not accelerating, they're just cruising at a constant velocity, the normal force on their feet also equals 100 newtons. However, in the bottom picture, they're accelerating up. So the normal force on their feet has to be bigger than 100 newtons so that they have a net force acting up on them. And in the topmost picture, they're accelerating down. So the normal force has to be less than their weight. When you're accelerating down in this elevator, the normal force on your feet is less than your weight. It is less than the gravitational force on you. And when you're accelerating up, the normal force on your feet is greater than the gravitational force on you. There's a net force up on you when you take off from the lobby floor. Now, this implies something, right? My claim here that I'm making is that how heavy you feel is not a matter of what your weight is, but it's a matter of what the normal force is on your feet. You don't actually feel the gravitational force acting on you, which is something I'll get to a little later. All you physically feel is the normal force pushing up on the soles of your shoes. So in this bottom picture here, when the normal force is bigger than your weight, you feel heavier than usual. And in this top picture, when the normal force is less than your weight, you feel lighter. If you can recall what it's like to be in an elevator, this is exactly what happens. When the elevator takes off and initially moves up, your knees might buckle a little. You feel like you're being pushed downward toward the elevator floor, and that's what it is to feel heavier. On the other hand, when you reach the top floor, you feel a little lighter and more, maybe a little fluttery or something like that in your chest. The ground, the floor, is not pushing up as hard on your feet as you're used to it pushing up. The normal force on your feet is lower than usual, and therefore you feel lighter than usual. Now, what would a scale measure in each of these three situations? I didn't draw the person standing on the scale, but we know that a scale would read the normal force exerted on the person's feet. So let's take a look at this bottom picture here. The y-axis will point up for us. And if I apply Newton's second law in the y direction for this person, I get the following. The normal force minus the downward gravitational force, which is equal to the person's weight, m times little g, equals the person's mass times the y component of their acceleration. If I solve for the normal force, I get mg plus their mass times their acceleration. Their acceleration is a positive value, so I know that the normal force is going to be bigger than their weight because I'm adding this positive value to number of newtons to their weight to obtain normal force. Okay, well, mg, their weight, is 1,000 newtons, as we've already calculated, and then we have to add their mass, which is 100 kilograms, times their acceleration, which is positive 1 meters per second squared, and this is 1,100 newtons. So the normal force on their feet is not equal to their 1,000 Newton weight, but rather it's 10% more than that. It's 1,100 newtons. This person will feel 10% heavier than usual. If we were to do the same analysis up here, we would end up, after applying Newton's second law, with the same exact expression for the normal force. But this time, when we add their mass times their acceleration is negative. It's downward, -1 meter per second squared. So the normal force on their feet will be 1,000 newtons minus 100 newtons, which will equal 900 newtons. Now the person feels 10% lighter than usual. The ground is pushing on them the same exact way the ground would push on them if they really did weigh 900 newtons. And if you're in a situation where the ground is pushing on you the way it would push on you if you did weigh 900 newtons, you are in the exact situation as a person who actually weighs 900 newtons. You'll feel lighter than usual. Now, I could draw a set of pictures when the person is moving downward. The situations basically get reversed. As you move downward, you feel lighter than usual. And when you reach the bottom floor, you need to accelerate up so that you don't crash into the sub-basement of the building. You feel heavier than usual. You always feel lighter than usual at the top of the elevator ride, regardless of whether your velocity is up or down. And you always feel heavier at the bottom of an elevator ride, regardless of whether your velocity is up or down. It's only the direction of your acceleration that determines whether the normal force on your feet is bigger or smaller than your weight. And this is provocative enough that I will give a special name for the normal force on your feet. Oh, that font is way too large, so let's lower that. The normal force on your feet is called your apparent weight. It is how heavy/light you feel. Okay, so in this example, the person at the on the lobby floor about to travel up will feel like they weigh 1,100 newtons. The scale that they're standing on would read 1,100 newtons, but when they approach the top of their ride, the scale reads only 900 newtons, and they feel as though they weigh only 900 newtons. All right, now here comes some of the very interesting stuff. I think you'll agree. I'm using the term apparent weight. Apparent means, you know, it's an illusion or something like that, right? Like, oh, the person feels like they weigh 1,100 newtons, or they feel like they weigh 900 newtons. To them, that's apparently what's going on. But their actual weight is 1,000 newtons the entire time. Right? In an introductory physics course, things are usually presented in that way. Apparent weight has this subordinate role in explaining what's going on relative to the concept of just weight, the actual gravitational force acting on the person. However, this perspective unfairly privileges the Earth reference frame. And we discussed back in September that it's a grave mistake to privilege the Earth reference frame above other reference frames. Let's think about the reference frame of the elevator, the reference frame inside the actual elevator. So I wonder if I can, is there a quick way to move all this stuff? Oh, I think I can just highlight it. Okay, great. And I'll move this down. Want a clean palette over here. Okay. I'll delete some of this. And eraser, this. Okay. So let's think about what this situation is like in the reference frame of the elevator itself. All right, this is the Earth reference frame. In the Earth reference frame, the normal force on the person is 1,100 newtons, and the gravitational force on them, their weight is 100 newtons. This is in the Earth frame. How about the elevator frame? Okay. In the elevator frame, let's see if I could duplicate this again. Very well. In the elevator frame, it's not apparent to the person at all that they're accelerating. In the reference frame of the person's body, they're never actually accelerating or even moving. It's always the environment that is doing all the motion relative to you, the observer. So when this person stands on a scale, oh, just to make this a little more concrete, suppose you fell asleep and when you woke up, you mysteriously found yourself in a metal box. Okay, you find yourself in a metal box. And you know that you weigh 100 newtons. Okay, sorry, 1,000 newtons. Did I write 100 before? I hope I didn't drop a zero. That would be a problem. 1,000 newtons, yes. I think I wrote 100, but it should be 1,000. All the gravitational forces should be 1,000 newtons. The person's mass is 100 kilograms. All right, so you wake up and you're in this metal box. And you don't know what happened. You don't know where you are. You figure, oh, I've been kidnapped or something like that, and someone has put me in a big metal box. And your presumptive captors have left a bathroom scale in the box. That's all they gave you. So you stand on that scale, and that scale reads 1,000 newtons. You know that the normal force on you is 1,000. Sorry, it reads, I'm sorry, 1,100 newtons is what I mean to say. And therefore, you know the normal force on your feet is 1,100 newtons because everyone knows that's what a scale reads. The normal force acting on your feet, 1,100 newtons. All right, now in your reference frame, you are not accelerating. In your reference frame, you're not accelerating. And because you're not accelerating, you know the net force on you is zero, which means your weight must be 1,100 newtons. How did you conclude this? Well, you stand on the scale, it reads 1,100 newtons. In your reference frame, you're not accelerating, so the net force on you is zero. You're just applying Newton's second law to your own body, and therefore you know your weight must be 1,100 newtons. So let's think about what's going on here. This is the same situation, just viewed from two different reference frames. In the Earth reference frame, the person's weight is 1,000 newtons. The normal force on their feet is 1,100 newtons. And so there's a net force on them, making them accelerate up. And we say their apparent weight will be 10% larger than their actual weight. In the elevator frame, the scale reads 1,100 newtons. But from their point of view, they're not accelerating. So they will conclude that they actually weigh 1,100 newtons. And all they actually feel, they will feel as though they weigh 1,100 newtons, as we previously discussed. That's how heavy you feel, whatever the scale reading is. Now, considering that they knew before they went to sleep that they weigh 1,000 newtons, and suddenly they feel 10% heavier, and the scale reading is 10% higher, they could conclude one of two things. One thing they could conclude is, oh, maybe I'm in an elevator. Maybe I'm on Earth in an elevator. But there is something else they could conclude. Pause the video and think, what else could their situation be? No pun intended, think outside of the box on this one. All right, maybe you came up with a conclusion that they could conclude that they're not on Earth. After all, if the normal force on their feet is 1,100 newtons and they're at rest and not accelerating, their weight must be 1,100 newtons. Well, they weigh 1,000 newtons on Earth, but wherever they are must not be Earth, I guess. The gravitational force on an object equals the mass of the object times the local gravitational field. That could be the field of the Earth, the Moon, Venus, wherever you're located. So their 1,100 Newton gravitational force that's pulling them down is the product of their mass and little g. And little g now equals 11 newtons per kilogram. So they could conclude that they are on a planet where the gravitational field is 10% stronger than that of Earth. That explains why they feel 10% heavier. That explains why the scale reads a 10% higher number of newtons. You see, for the person inside the elevator, it's not merely their apparent weight that is 1,100 newtons. But for all intents and purposes, their weight truly is 1,100 newtons. This raises the somewhat uncomfortable fact that the value of a gravitational field depends on your reference frame. So the gravitational field outside the box is the gravitational field measured by an observer who sees the person riding the elevator. And that is the good old familiar 10 newtons per kilogram. But the gravitational field inside the box is equal to 11 newtons per kilogram. And from the point of view of the person inside the box, they multiply their mass by that value to figure out how heavy they feel and how much the scale reading will be. So with an elevator accelerating upward with a great acceleration value, I can simulate a very strong gravitational field for the person riding the elevator. Similarly, given an elevator with a substantial downward acceleration value, I can simulate a very weak gravitational field for the person inside the elevator. And when I say simulate, from my point of view, I'm doing them the favor of simulating a weak gravitational field. But from their point of view, they are actually in a weak gravitational field. And neither perspective is preferable to the other. All right, one more thing here. Suppose I wanted to simulate what it would be like in deep space. In deep space, there is no gravitational field present. You're very far away from planets and stars. In deep space, there is no normal force supporting you because there's nothing around at all supporting you. How do you think I could create a situation where there is no normal force acting on the person in that elevator? Because if I can do that, I can simulate for that person exactly what it's like to be in deep space, an astronaut in deep space. Pause the video and think what I can do to simulate deep space for the passenger. All right, well, what I can do is I can cut the elevator cord. Then the person inside the elevator will be in free fall. The person has a mass m, and there's a gravitational force pulling them down equal to mg. And there is no normal force pushing them up. They are falling with the same acceleration value as the elevator and the same acceleration value as the bathroom scale. And the person and the scale are just kind of floating at rest relative to each other. There is no normal force on their feet. Well, this is what things look like from the Earth reference frame, at least. If I do a split screen and we think about what things look like from the elevator frame, there would be no forces whatsoever that I would draw in this free body diagram. In the elevator frame, the person's acceleration is 0, as is the physical scale's acceleration. The scale and the person are kind of hovering above the ground. There's no normal force on the person's feet, and there had better be no weight that the person experiences. Otherwise, the person would accelerate, which they are not doing from their point of view. So in the Earth frame, the elevator is accelerating at the free fall acceleration value of 10 meters per second squared, or 9.8 meters per second squared, because there is one and only one force acting on them, their weight. But in the elevator frame, they're not accelerating, and they experience no forces whatsoever. This is the clearest argument I can make to back up the statement that all you ever feel is the normal force on your feet. You do not feel your own weight, because the passenger in this elevator feels quite weightless, just like an astronaut in deep space would feel weightless. Even though in the Earth reference frame, they most certainly have a weight, they don't recognize it as such, and they don't feel it from within the elevator. Yeah, so the existence of a gravitational field, the existence of a person's weight is very much a reference frame dependent quantity. And that brings up the idea that gravity, the phenomenon of gravity itself, is a reference frame dependent quantity. It's not an absolute phenomenon where everyone will agree on whether gravity is present or not present, and everyone will not agree on exactly what the strength of the gravitational field is, and therefore what the weight of objects are across multiple reference frames. In the Earth frame, gravity exists and explains this person's free fall. In the elevator frame, gravity doesn't exist, and that explains for the person within why they're floating. Okay, I'm going to link to a video on this. This is the basis for Einstein's general relativity, which he published in around, I think it was 1916. And he explained exactly what the phenomenon of gravity is really all about. It's actually not about forces at all. Although in this course, we treat gravity as being a force, it's a very funny type of force if it is one. It's a force that I can make disappear by jumping into an appropriate reference frame, specifically a free-falling reference frame. In a free-falling reference frame, gravitational forces completely vanish. And there is a sense in which a free-falling reference frame is the most natural kind of reference frame from which to analyze a situation. So I'll link to that video, and then you can try the associated homework, and I will see you in class on Monday. Have a great one.